Good afternoon, and welcome to today's TSP2 Bridge Presentation webinar. My name is Rod Thornton, and I'm with the Maryland Department of Transportation State Highway Administration, and I currently serve as the chair of the Northeast Bridge Preservation Partnership. I will be the moderator for today's panel session. The topic of today's webinar is repairing cracked, damaged steel bridges. Our first topic, cracking and repair methods, will be presented by Rama Krishnagiri, Managing Director, Assistant Vice President at WSP USA, Jordan Coleman, EIT, Structural Engineer at WSP USA Incorporated.
All right, thank you very much. We sincerely appreciate this opportunity and our sincere thanks. I'll be splitting the presentation today with Jordan, Mike Abrams, and Alex Kluka in the audience, and they've been involved in this project from the beginning and continue to be involved. We will focus today on sharply skewed steel bridges, moderate to sharply skewed steel bridges with either straight or flared girders. There are some commonalities in these bridges that we'll be discussing. The diaphragms or cross frames are non-contiguous. Some of the decks are horizontally curved, but the bridge girders themselves are not curved. They're straight or they're flared. We'll look at bridges. Essentially, they're all over 60 years old. They were all constructed in the mid-60s or so. Although we had 14, 15 case studies, we narrowed them down to a few for today's discussion. We'll also look at some existing retrofits on these issues found in the field and how they've been performing. And we'll definitely discuss one additional cost-effective option that we are looking at. Also analyze, which we have in detail, and Jordan will be discussing that. Okay, we've seen a pattern of cracking in heavily skewed steel bridges. We've been doing these inspections over several years, and when we first started to see this, there was a pattern, and not only was the cracking somewhat similar, there were several commonalities in these bridges. The diaphragms were staggered. We had this classic web gap detail because the connection plates were not fully connected to the tension flange. And the skew was definitely a factor because of the differential live load deflection, which caused some pretty heavy cross-frame forces, localized stress concentration at the toe of the connector welds, and subsequently ended up with cracks in the web weld as well as in the base material. Skewed steel bridges, as you can see here in this slide, the live load response, live load deflection across the cross section is not uniform. In other words, if you take a cut section across the width of the bridge, the 10th points of the girders don't line up. So the differential deflection introduces out of plane bending and large cross-frame forces, especially when these diaphragms or transverse connection or transverse members are not in a continuous line. So that stress concentration at the toe of the connections, welded connections, causes large stresses leading into cracks. And that's pretty much what we have found on all these bridges. Here's a classic detail that we'll be looking at. As you notice, the connection plate terminates above the tension flange, the bottom flange in this case, because most of all the bridges in our study were simple supported bridges. Back in the 60s, no welding was allowed to the tension flange. So when these connectors were indeed extended down to the flange, they were just tight fit. So there was no positive connection. And all the case studies that we have are of this nature. So let's look at bridge number 1. The geometry was a 4-span, simply supported bridge, 31-degree skew, a moderate skew, staggered channel diaphragms with cut short connection plates. You'll see this over and over, so bear with me. What did we find on this? Numerous cracks on the girders, pumping of the bearings. One common situation or common structural condition on this is that the bearings were all rocker bearings or pinned fixed bearings, allowing only a single direction of rotation or movement. So that restraint also had an effect. And we saw that many of these bearings were themselves pumping, so they weren't fully seated. That and then the cracking of the girders themselves, the web base material and or the welds. This is on bridge number 1, where the end diaphragm was just welded on to the end of the web, a very rigid connection, obviously. And then the bearing itself, as you can see, the rust stains at the pin shoulder indicate that vertical movement. And this bearing was more or less twisted, floating for a good part of the contact area due to the twist. And the girder itself was shifted somewhat within the limits of what the shoulder clearance was. It was favored to the one side. The classic twist that I mentioned, the left picture shows the fixed end where the rotation is counterclockwise, as you can clearly see at the shoulder and the sole plate interface. And the right side picture shows the expansion end where it's in the opposite direction, a rotation of the sole plate relative to the pin. And then, of course, a pumping action under live load, heavy live loads. All right, the next bridge was a horizontally curved deck, but with straight girders to make up the curvature. We have seen many bridges of similar construction from the 60s where the deck would be horizontally curved, but the girders would not be. They would have flared girders to make up the curvature. This was one such bridge, 1,200-foot radius. A framing of that bridge, 30 degrees skew, non-contiguous diaphragms, full depth cross frames in this case, X-type cross frames, but the connector plates were not positively connected. And we found a lot of cracking on this bridge, typical distortion-induced fatigue cracking. At the toe of the weld, when our inspector first saw this a few years ago, the first crack when he noticed, we alerted the owners and we did a more in-depth of each diaphragm hands-on. And sure enough, out of the 700 odd such typical connections, we found about 140 of those had cracking, either in the base metal propagating into the web to flange weld or in the weld itself where it was starting to crack. One such girder here on the connected side, the crack started down at the toe of the weld and went straight up along the web and also propagated into the flange to web weld. So it was more like a T crack. And then on the opposite side where you don't have the diaphragm, the right side picture shows how the crack extended into the web vertically from the flange on up. One of the simple retrofits for such crack distortion-induced cracking is arrest holes. Well, that's what was done on one of the bridges, and clearly the tip of the crack was not 100% accurately located. So subsequently, the next 2-year cycle, when we went back, we saw that the crack had, it was not necessarily the second cycle, but third or fourth, but the crack had kept growing. The crack was never located accurately. So in a retrofit where crack arrest holes are used, the most important aspect is to locate the tip and then the right tools for cutting out the hole, grinding off the hole and such. But we have seen this occur in quite a few places where the tip was likely not located 100%. But then we look at this where we had spider cracks on the same bridge, on a similar bridge. Some of the crack holes are working very well where they arrested the cracks from propagation. But then at these tight corners where you had a 90-degree intersection where the pen points here, the red tip of the pen shows the propagation beyond the hole. So that is something we have been also seeing on these bridges. Then the group of bridges 3 through 6, built in the same age, same time, same sort of details, same material for the steel, again 60 years old, The skew was the only variable. The smallest skew was about 28 degrees in this group of bridges, and the most sharpest skew was about 51 degrees. Rocker, pin bearings. What you see here in this picture is a repetition of the other bridges as well. And here's a plan of the most sharply skewed bridge with a railroad crossing underneath, 51 degrees skew, and the standard type of cross frames, staggered diaphragms that was used on all these bridges. The local stress concentration at the toe of the weld due to the cross frame forces, when the cross frame tends to want to rotate due to differential deflection, it puts a very large stress at the end of the weld, and there's no continuity of the weld there, and that large stress concentration causes the starting of the crack, and we saw that on many of these welds. Another bridge, full depth cross frames. I don't need to go into the details. You've heard enough of that, but here's what we found. You've seen enough of these as well. Again, notice that the stiffener or the connection plate is just a tight fit, not positively connected. Very typical defects, very typical cracking, spider cracking in this case, extending from the toe of weld into the base metal, pumping of the bearings, again a twisting of the bearings, which you can see if you look closely at the shoulder area of the rocker. I'm sorry, the pin. You'll see that there's a differential between the sole plate and the interface there, indicating that pumping action or a floating bearing. This is a typical retrofit. The size of the holes is important as well. In New Jersey, we typically use 1-inch diameter holes. We use annular tip, carbide tip annular cutters, and then we also grind the hole using a 120 grit sand flap to make it smooth after the hole is drilled. But on the left side, the holes were successful in arresting the cracks. Holes were done at the same time, whereas the right side, similar repairs, but the crack propagation continued. So the post drilling testing of these metals taken out would have probably helped alleviate the situation, but that was probably not done. And the UT testing that is mandated before and after drilling of the cracks typically should be done on both faces of the web to ensure that the tip is caught. And if that didn't happen, this is what ends up happening, crack propagation. Causes, then we looked at enough of these cross frames, the differential deflection, the lack of torsional rigidity. Cross frames in a discontinuous line introduce larger cross frame forces than if they were in a single line. The web itself is inherently weak where you have one side connected, one side not connected. When the cross frame is set too close to the end of the girder, the end panel gets very rigid. On top of that, you have connections of the diaphragms to the web. Then the rocker bearings and pin bearings make it even more rigid because it only can go in one direction. So all these together and the restraints that we cause by this ends up with the cracking of due to differential deflections. In a case of the deck being curved and the beams being straight, the torsional effects may not have been considered in design. And most of these cracking is due to the unanticipated participation of transverse members with longitudinal members, not accounted for in design. Back when we were using standard cross frames before the consideration for skewed bridges, they used to be standard 3x3 angle members. That's what would be used. So the rigidity of those comes into question if it was not designed for these large forces. One retrofit that seems to have worked well in our cases is a stiffening option. When we have stiffened by extending the cut short plates and connected it to the tension flange with enough number of high strength bolts, both in the flange and the connector, we have seen that subsequently either the cracks have stopped or no new cracks have formed. This is eliminating the small web gap detail has worked well so far, and that has been done on many of the bridges. With this, Jordan's going to discuss the analysis we did on a pair of bridges to look at what I discussed so far and back into the analysis, and also look at elimination of the cross frames completely. And Jordan is going to pick up from this point.
Thanks, Rama. So just as Rama touched on, we believe a lot of this premature fatigue cracking that we're noticing on a lot of skewed and splayed bridges is predominantly caused by distortion-induced fatigue. So distortion-induced fatigue is caused by out-of-plane distortions or deformations that create large secondary stresses that can build up in fracture critical or fatigue prone connections. Unfortunately, those secondary stresses aren't something that is readily calculated or easy to quantify. It's not something that's determined from doing a 2D or line girder analysis. And it's often neglected during a standard design procedure because normally people consider them to be negligible. You know, as Rama touched on, we're finding that some of these stresses can be pretty significant enough to cause some premature cracking. As I'd mentioned, there's no real cut and dry way to quantify the stress ranges caused by distortion-induced fatigue. And the recommended course to go through and do that currently is to do a 3D finite element analysis. Which is what we did for bridge number 4. So Rama briefly discussed bridge number 4, but I'm going to go into a little bit more detail. Bridge number 4 consists of 2 identical twin structures. These structures carry the northbound and southbound traffic of a large interstate highway over a county road here in New Jersey. Both, like I said, the bridges are identical in every way, in framing, span length, skew, the details on the bridge, even with average daily truck traffic. And they are also pretty consistent with the pattern of cracking that was identified in the field during our inspections. So the skew on the bridge is about 35 degrees. Both bridges are multi-girder steel composite simply supported bridges. On one end you have rocker bearings. And as you can see, the diaphragms are staggered throughout the framing plan. Cracking was noted in most interior diaphragm connection plates, and it was also noted on the end diaphragm connection plates at the toe of the welds of those connection plates. So on your left, you can see the end diaphragm connection plate detail, and on the right is the intermediate diaphragm connection plates detailed. So as I said, at the toe of the welds of those connection plates in the web of the girder is where we were seeing the cracking occurring. For the intermediate diaphragms, at the time that this bridge was built and constructed, welding to the tension flange was not allowed by the code. So in some places you have as large as a 2-inch gap separating the bottom of this diaphragm connection plate to the bottom flange. Both of these details are considered an AASHTO Category C prime detail, which gives us a constant amplitude fatigue threshold of 12 KSI per AASHTO. What this essentially means is that AASHTO allows 12 KSI of stress range in those connections, below which you can assume infinite life for the connection. If the stress ranges go above 12 KSI, you do have to consider the finite life of the detail, which can significantly reduce the overall life of the bridge. So just to briefly go over the process that we used to create these models and how we went about analyzing bridge number 4. We used Midas Civil 3D to build our 3D finite element analysis. As I mentioned, the bridges are identical in every way. So just to save us on some time and computer bandwidth, we only fully modeled one of the twin structures. We referenced the FHWA manual, the design and evaluation of steel bridges for fatigue and fracture, to help us figure out how to do the tight knit mesh. Every single element on the bridge was discretely modeled for the superstructure, and they were all modeled using shell or plate elements. And rigid links were used to model the shear studs in order to model the composite action of the deck. And they were also used to discretely model the bolts connecting the diaphragms to the diaphragm connection plates. So on your left is a 3D isometric view of the model that we built. Again, the substructure was not discretely modeled. We used nodal supports to, accurately model the stiffness of the substructure. but every element was discretely modeled as a shell or plate element. So that includes the deck, the girders, the diaphragms, the diaphragm connection plates, the intermediate stiffeners and the bearing stiffeners, absolutely everything. On the right, you can see the mesh size that we used in order to evaluate this. So the FHWA recommends choosing a mesh size that's extremely fine in comparison to what we normally would do, but it's usually based on what the thickness of the material is that you're analyzing. So we used a 1-inch fine mesh. If we used the 1-inch fine mesh on every single plate in the model, my computer probably would have caught on fire. So because all of the cracking was localized to these connection plates, and specifically the toe of the welds, on 6 inches of either side of each connection plate, we used that fine 1-inch mesh, and then we gradually made the mesh size coarser. So we graduated to a 5-inch mesh and then again to a 10-inch mesh. And the only reason we did that gradual increase was to make sure that none of our data was skewed due to the fact of having an abrupt change in mesh size. So overall, we built and ran and analyzed 7 different models to look at different conditions, service conditions, and retrofit conditions. So the first model was an as-built model where the rocker bearings acted as true expansion bearings as they were intended in design. The second as-built model that we ran restricted the lateral movement at the rocker bearings to mimic what's actually happening in service. The third model was what we called an as-inspected condition. It's the same thing as the second as-built model, but we also went through and discretely modeled in the cracks that were noted in the inspection report, just to get an idea for how the stiffness of the system was changing and how any stresses were being redistributed due to the fact that there are now cracks in the web. We ran 4 different retrofit models. The first retrofit model is a system softening model where we loosened the bolts that connect the diaphragms to the diaphragm connection plates. So the intent of this is to reduce any sort of force transfer from the diaphragms to the girders themselves. The fifth model, we modeled in that web stiffening detail that Rama briefly touched on. We modeled in plates connecting the bottom flange of the girder to the diaphragm connection plates, stiffening the connection up and creating that positive connection to the tension flange. The sixth model was a combination of models 4 and 5, and the last model was also a system softening model, but we fully removed all interior diaphragms. And I'll get into all of these in a little bit. So what you're looking at on this slide is the deflected shape of one of the interior girders deflecting under the HS-20 fatigue truck. And as expected, there's a pretty significant amounts of torsion and out of plane twisting in this girder. It almost kind of looks like somebody is literally twisting it on either ends. So it's pretty significant, and all of that deflection is going to be transferred predominantly through the diaphragms. And there's also going to be a differential deflection of these girders, and those differential force effects will be transferred to each one of the girders, and explains why we're seeing a pretty significant amount of secondary stresses at those diaphragm connections. The other thing to note here is that the girder kind of has the tendency to rotate at the end. It's a little hard to see, but you can see it in this photo. It would explain why we're seeing some cracking at the end diaphragm connections as well, because the rockers are going to be restricting that tendency to want to rotate. These are the stress ranges for a standard interior diaphragm connection and the stress range at the toe of the weld of those connection plates. We found 34 KSI of stress range at the toe of the weld. It's almost 3 times more than what AASHTO allows. Just to reiterate, for the C prime details, AASHTO has a constant amplitude fatigue threshold of 12 KSI. So it validates what we were finding in the field with pretty significant cracking and also this premature cracking as well. When the rotation at the rockers is restricted, we are finding a 17 KSI stress range as well at the toe of the weld there, which again exceeds the 12 KSI constant amplitude fatigue thresholds and would explain why we were seeing some premature cracking. When that lateral restraint is removed and you allow that rocker bearing to act as a true expansion bearing, that stress range goes all the way down to 5 KSI, which is well below 12 KSI and allows you to assume infinite life for the connection. So just to illustrate how significant the restriction of lateral movement is in this location. So now I'm going to go into more detail about the retrofit cases that we examined. Overall, we looked at a combination of 3 different retrofit options. The first was the web stiffening option, which Rama also previously touched on. Essentially, it consists of taking some sort of bent plate or structural T or angle and bolting it to the bottom flange of the girder, and then bolting it to the diaphragm connection plate to create a positive connection. Diaphragm bolt loosening is a system softening retrofit, and by loosening the bolts that connect the diaphragms to the diaphragm connection plates, you can reduce the amount of force those secondary stresses are being distributed from the diaphragms to the girders. And the last option was also a system softening option. It consisted of full removal of the intermediate diaphragms, which again was something that we could consider because the intermediate diaphragms do not contribute to the live load distribution in the system. So it sounds dramatic, but it is totally feasible. So again, just to go into some more detail on the web stiffening, like I said, it consists of some sort of bent plate or structural T that has at least 4 bolts in the bottom flange and 4 bolts in the diaphragm connection plate to create a stiff connection to the tension flange. This is a relatively standard detail presented in the FHWA manual for repair of steel bridges, and it's also an AASHTO category B detail, so you actually get a little bit more constant amplitude fatigue stress threshold to work with. You actually get 16 KSI to work within as opposed to the 12 KSI of the as-built detail. So when we model that positive connection, we see that the stress in the toe of the welds pretty much dissipates. There's a little bit of a stress riser where the geometry of that connection plate kind of dips down to meet the tension flange. But with proper detailing, that can probably go away. So the model just proves that it's a really effective retrofit option. Like I said, it pretty much eliminates the stress range at the problem locations. And this is something that we have implemented on bridge number 2. Subsequent inspections prove that the cracks that were previously identified have not propagated past where they initially were, and no new cracks have initiated since installing this retrofit. So the model shows that it's effective, and it's also shown to be effective in practice. So bolt loosening was another retrofit we looked at. Like I said, it fully depends on the theory that you reduce the force transfer from the diaphragms to the girders and thus reduce the stress range at the toe of the welds. Research done by the FHWA, however, does indicate that this is quite variable. It's very idealistic in its approach. It may not actually be super feasible depending on your case. If the bolts are already in bearing, loosening them will not change anything. Again, bolt spacing, the layout of your bolts and the number of bolts, even the type of bolts can all affect how effective this retrofit is. So there's quite a number of variables that go into the bolt loosening retrofit. When we modeled only the bolt loosening, it does reduce the stress range, but not enough to actually be helpful. It does go down from 34 to 27 KSI at the toe of the weld, but it's still more than double what AASHTO allows for this type of detail. So it does help, it does work, but not enough, theoretically. In practice, there's also way too many variables that can go into whether or not it's actually effective. The last retrofit we looked at is another system softening case, but it was full removal of the intermediate diaphragms. Because these secondary forces are really being caused by the force transfer at the diaphragms, removal of the diaphragms should, in theory, also remove those stress ranges, those high stress ranges that we're seeing. So it sounds dramatic, but the intermediate diaphragms are really only required for steel erection to stabilize the girders during the concrete pour. Because this is a composite system, once the deck is cured, the deck itself is going to provide a pretty significant amount of stiffness, and it's the deck that's distributing any live load to the girders themselves. The live load distribution factors for straight and skewed bridges don't account for the diaphragms for live load distribution. Just one thing to note, these bridges are simply supported. There is no negative moment region. If you have a bridge with a negative moment region, additional analysis may be required. just because those intermediate diaphragms play a very important role in bracing the bottom flange so it doesn't buckle in those negative moment regions. That wasn't a concern for us, so we pressed forward. And again, it pretty much eliminates the stress riser at the toe of the weld. We get a similar stress range to what we were finding for the web gap stiffening detail. However, this can be significantly more cost effective because all we did was remove the diaphragms. We did leave the diaphragm connection plate in place, and we just did this as a consideration for the fact that if there is a plan for a future redecking, either the diaphragms that came off will have to go back onto the bridge, or temporary diaphragms will need to be installed to support the girders during a concrete pour. However, again, the stresses at the toe of the weld were effectively reduced. And just to reiterate, this was an analysis on a simple span composite structure. In negative moment regions, additional analysis is required to see if this is feasible, potentially looking at where the points of inflection are to make sure that in negative moment regions, there is something bracing the bottom flange. So we also did a load rating analysis on this bridge just to see what effect these retrofits would have on the load ratings. The as-built was rating pretty well, almost at 50 tons for the HS20 truck and LFR, and 1.25 for HL93 and LRFR. But to point out, once you remove the diaphragms or really perform any retrofit on the diaphragms, it effectively doesn't change the ratings at all. And the reason for that is the diaphragms really only play a role in the non-composite dead load case on these bridges. And since they were there during the non-composite dead load phase, removing them doesn't affect the live load at all. So essentially the load ratings, go unaffected as well. So just some further considerations. The diaphragms do play a very important role in lateral load distribution. So if there's potential for collision, or if a bridge has a history of impact or collision, obviously special care must need to be taken before considering this retrofit, whether that's hosting the bridge or taking additional routes to ensure that certain traffic doesn't go under the bridge or near the bridge. The other potential is to utilize some sort of lean-on bracing technique where there is bracing in the first bay just to distribute that impact force from the fascia girder to the interior girder. And the same goes for any high wind locations. Additional care will be needed before considering this retrofit option. The other consideration, essentially record keeping of the diaphragms once they are removed. If the intent is to keep the diaphragms once they come off the bridge for future redecking, it might be a large-scale record-keeping dilemma. If the intent is just to recycle them and put on temporary diaphragms, it's a moot point, but it's still something to keep in mind. But overall, it's just as effective at reducing the stress ranges, at stiffening that detail, but it can be a cost-effective solution if implemented correctly. So just to conclude, in skewed bridges, a significant amount of secondary forces caused by out-of-plane stresses can concentrate on those fatigue-prone connection plate details, causing premature cracking. The skew of the bridge and the rocker bearings can exacerbate that quite significantly. We found that the bolt loosening on its own was not an effective retrofit in the situation. It was just, there's too many variables that go into it, and it just didn't do enough. The system stiffening proven to be effective. We also had a 6-minute presentation. The interior diaphragm removal showed to be just as effective, but can be more cost effective. The other thing to note is that crack drilling can be an effective short-term solution, but proper UT testing to identify the crack tip location is essential to ensuring that it goes well. And that's all we have. Thank you so much for listening to us.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.